guess definitely woken up for like there's 7 of you here. I got there at 8:05. So I guess you could probably to the fact that would not work. It might work. I had something like last semester where we would just sit in that room for like 3 hours alone. The one of us get our office hours and there's no assignment to do. Yeah, that was the time that we both had to be at the same time.
What's that? Yep. Thanks, Carlos. How's it going?
Good.
Good. Good break?
Yeah, it's fun.
Good. Anybody go anywhere great?
Went to Colorado.
Is that great?
That was great. It's better than great.
That's awesome. Well, we can get started. So, welcome back. Hope your break was great. Some time off. Also, the canceled class on Tuesday. Good job getting all your homework in. Most everybody got it in on time. A few lates, but good job there. Homework 3's out there. We've already covered all the material for homework 3 if you haven't looked at it yet. So you can get started on it right away and get ahead there. It's now PyTorch, so hopefully you'll enjoy using that and not have to get deep into the weeds there. Today we're going to shift gears. We've been kind of doing everything in the context of image data sets, computer vision, convolutional neural networks. And we're going to start looking at a different class of neural network known as recurrent neural networks. And these have a different kind of like inductive bias, as we've called it, where convolutional neural networks, this is all about the way that the architectures are put together. It's all about modeling things that are expected to have spatial structure, localized structure within things like images. Now, convolutions can be applied to more than that, but the idea of like a filter being this kind of local, this local like feature extractor that is applied, all over the image, is some way of saying what we expect in this data is for the information to be localized, to be translation, or we want it to be translation invariant in the sense that, if you think about an image, if the cat's up here in the upper left-hand corner, the bottom right-hand corner, then we want to be able to extract that in either case, and that we want to, over successive layers, sort of integrate that together into a full picture of the image. With recurrent neural networks, the idea is more that the inductive bias is geared towards sort of sequential data. So the idea being that we might have a sequence of data points. The canonical example here is language, but also you can think of most time series, things like that, where the idea is that you're building up kind of representation of your data, data point by data point in a sequence, and that you want to be able to encode that somehow, so that when you use that model, it's not only encoding information about individual tokens, say like words or characters in a sentence, but that the characters are following each other, or the words are following each other in a certain way. So this is the inductive bias here. That inductive bias is matching something like what we'd expect, say, from language, right? That like the meaning of a sentence is about the the way that these tokens, like for instance these words, kind of follow each other in the sentence, and that's how we want to encode the information. So so that's where we're going to go. We'll do that today and all of next week, and then the following week we're going to look at a different network architecture, the transformer, that's also been used very successfully in language. There's the language transformer is kind of, or sorry, just transformers in general are really more about like set to set matching. So rather than like sequences or sets, but you can build in the idea of sequences in the way that you, in some of the details of the architecture, and we'll be looking at that. And really truly, like I've said a couple times before, you know, the transformers in many, many ways have sort of become the architecture of choice for language and for, you know, many other kinds of sequential data sets or data points. And recurrent neural networks sort of taken a bit of a back seat as a result. But they're still out there. There's still a lot of, you know, use of them, at least, you know, historically, like a couple of years ago. And you'll still see a lot of it, you know, just in papers and things that you look at. But you know, really for like state-of-the-art work, you'll mostly see transformers being used for sequential data. Yeah, but with that, we'll get going on this. So, like I said, there will be 3 lectures on recurrent neural networks. So today and next Tuesday, and then a week from now, Thursday, we'll look at how recurrent neural networks really set the state of the art in terms of like a really interesting and important application of using what we call machine translation, or using computers to translate from one language to another. That has again been surpassed by the use of transformers, and the state of the art is with those kinds of architectures, but it's good to go through and know something about this, since it's part of the common kind of knowledge in neural networks. Okay, so thinking about this a bit like abstractly, what are the kinds of neural networks that we could have? Well, let's think of them in terms of like their inputs and their outputs. Kind of so far, what we've been doing looks like this. We have one input, an image, and then one output, or label, or class, as we've been calling it. And for ImageNet, that would be like the object that's in that image, like the label for that. Or pretty much kind of like most simple supervised learning tasks kind of look like this. And it's one of the reasons why oftentimes when people are looking at like neural networks and deep learning, you can often think of this as like function approximation. What we have is we have like a family, our neural network is really a family of neural networks, right, depending on which parameters you choose. And that when we're doing optimization, we're really trying to find the function within that family of possible functions that best takes us from our input to our output. Okay, so this kind of one-to-one, one input, one output. We talked a bit about how you can have like multiple heads on this, so this could be like many to one, but you could think of kind of each one of those as like its own one-to-one network. But there are lots of different ways that we could think about this. So we've looked at this example already, this one-to-many, right? Where the example being image captioning, where the idea was that we had a single input, the image, and then the output was a sequence of words that was the caption. Okay, so the output of the network was not, maybe you could think of it just like a single sentence, but really what these do is they output multiple tokens corresponding to the words for the caption. We haven't talked much about like how that's actually done. That's what we're going to start talking about, starting today and over the next couple of lectures. So an example of a single input to many outputs. Here are some other examples of tasks that have this sort of different structure. So many to one. So one of the things that we'll be able to do with recurrent neural networks is to take sequential data like a sentence, and then be able to sort of like classify it in some way. And one of the kind of canonical examples of that is what we call sentiment analysis. So it's like, what's the sentiment of this? It's often like tweet or some short, like set of words that are maybe part of a social media post or whatever. But the idea being like, is this saying something positive about the subject of this, this sentence? Is it saying something negative? Is it neutral? It's actually a really difficult problem just because language can be really ambiguous in these ways. But the idea is that you have your sequence of words in your sentence, or your paragraph or whatever, and you're trying to classify. You're trying to say, okay, is this positive? Is it saying something positive about the subject, negative about the subject, neutral about the subject? You could also, you can easily imagine how to extend that into other kinds of things, like maybe does this express a kind of emotion? You can go through like classes of emotions and things like that, right? So that's an idea this is a class of networks where we take multiple inputs and we want one output. And then there's just like lots and lots of problems that look like many to many, where we have some input, like the canonical example here is translating from one language to another, where we have the input is, say, a sentence in French, and the output we want it to be the corresponding translated sentence in English, or whatever paired languages you want. And you can imagine how kind of complicated this gets, because for some languages the grammars are very similar to each other, right? And there's like words, there's cognates, very similar words in both languages that mean the same thing. But for many of pairs of languages, that's very different, right? The grammars are different. The alphabets are extremely different. I don't know, there's lots of differences. So like this can be like more difficult or less difficult depending on how much the two languages share in common, or more generally like the sequences you're trying to translate one to another. But nevertheless, like they all kind of fit into the same pattern. Another kind of common example here would be like forecasting, so like time series forecasting. So you have time series, say I don't know, something like weather or sales or something like that over a certain period of time in the past, and then you're trying to predict what that looks like in the future, right? So like what the weather might be 1, 2, 3 days out, or forecasting sales 1, 2, 3 quarters out, or something like that, right? And there's just tons and tons of time series, data sets, and it's very common. And this kind of task of going from one sequence to another is very, very common. And then just sort of like more generally, this many to many, which looks like one to one, but the idea is like as you see more and more examples, of this input, you're using all of that information to say something about what's not only in the current like the current context, the current input, but integrating that information about the past. So like one good example of this is to do something like the image classification problem, but you're really classifying video, so frames of images, and you want to be able to, at every frame, classify it, but you have more, because this is video, there's a natural time series of the sequence of the frames. You want to be able to use all of those frames in some way to classify the what's like maybe coming, what's coming next, or what's in each one of the frames. Anyways, the point is that, again, one of the really useful and cool things about neural networks is that they're very, very much like these reusable pieces. It's like having this great big bucket of Legos, and you can make all kinds of really interesting things out of them, houses, cars, whatever you want, because while individually, like these are all just little blocks, the way you put them together gives you, the final thing, and there's lots of ways that you can put these together. And remember, each one of these, when we're looking at these arrows, these are all giving rise to some notion of like a computation graph, right? So it's like, it's some way of saying, how do the outputs from these networks depend on the inputs and the intermediate hidden states? And that's really, in a nutshell, what neural networks are all about. And, the arrows tell you about how information is passed forward. And of course, we'll be back propagated. We'll go backwards through those arrows. Okay, yeah.
Of like the examples cases that we've gone through, are there any where like recurrent neural networks are still the way to go?
Yes. Usually when you have sort of less data, like transformers in general require a lot of, like if you don't have something already pre-trained, they generally will require a lot of data because there's a lot of parameters involved. I mean, you can get a lot of parameters here, but with recurrent neural networks, there's typically a lot of parameter sharing, and we'll see that here in a second. And so there's less parameters in general, and so they could do better, like just in terms of generalization when you have less data. And there are some very different kinds of recurrent neural networks, like that have all kinds of interesting rules of that gate the information from, say, like one hidden state to the next, that could actually fit your data super well. But it's not really clear that it's never really clear from the beginning, like whether or not that's the case. But yeah, I think in general, transformers are typically larger, they have a lot more parameters, and therefore just need more data.
Okay.
Yeah. To train well. I mean, to train something in general as well. Good question. Okay, so this has all just been kind of set up and talking about kind of abstract ideas. So recurrent neural network, what do we mean by this? So the idea is, why recurrent? Well, here's why recurrent. We will have an input, and then there will be this kind of, like this module, and there will be different ways of defining this, where the idea is we're going to let the output of this neural network, this neural network module kind of interact with itself. Basically, like output something and feed it back into itself, and do this multiple times, so that we can continue to build up a kind of like internal state as we change the input. And we're going to spend the next however many minutes kind of getting into what this looks like. What are we typically trying to do here? We're typically trying to predict something for each. We'll often refer to them as time steps. This doesn't have to be a time series, right? Like language, it's not really appropriate to talk about like a time series, but the idea is that there's some sort of sequential thing. There's some kind of well-defined sequence to the input, and so we'll talk about, we'll often refer to as time steps. So how do we do this? Well, what do we mean? Like there's going to be some kind of internal state here kept by this recurrent module, and in general, it's going to look something like the following. We're going to have some kind of input. This might be the teeth input, in our sequence. And what we've done so far is we've built up some kind of internal state depending on all of the inputs coming before it. So we refer to this as T-1 hidden state, which was going to depend in general on the inputs x1 through xt-1. And then we have some sort of function. This is typically going to be our neural network parameterized by W, and it will output. Its job is to take the current state and the new data point in the sequence and output the next or the new hidden state. So this looks a lot like what we've done in the past, in the sense of like having many layers, right? Where you can think of like these H's as being the feature maps as we go from one layer to the next and get deeper and deeper into the network. But the idea here is there's two differences. One is that at each time we do this, we're going to make the output of this depend on some part of our data, like the next point in our time series, or the next token in our sentence, or the next character in our word, or something like that. And unlike when we have layers in like a deep convolutional network where the parameters are different from layer to layer, like the filters are different from layer to layer, this is going to be shared. This W is going to be shared for every step. So it's going to be the same function that takes a data point, the current hidden state, and produces a new hidden state at every time step, at every point in the sequence. Yeah.
Sorry, just to make sure I'm understanding correctly. So would this be like if you have a month of weather data and you want to predict like a week out? So it's first going to predict tomorrow, and then the day after that, and then the day after that, the day after that, until you finally get to 1 week out?
Yes, that's exactly. Yeah, that's exactly right.
Okay, so then if I
like if T indexes days.
Okay, sure.
Right. Yeah. So implicitly, that's what you meant.
Yeah.
Yeah.
So if I only wanted to predict 1 day out, it would only go through this once.
Yes. So, but during at inference time, when we are predicting, yes. When you're training, no. Like you will have you'll have a fixed. You'll decide on some sort of fixed length of the sequence that you will require, to produce the final output of the prediction that you care about, and you'll get to that by inputting these one by one, producing a hidden state and the next hidden state and the next hidden state until you finally get to the point where you're ready to predict the next state. Well, there'll be some more diagrams that kind of make this a little more explicit, but it's a great question. So yes, in general, what you've asked, what you stated was right. If I'm going to predict many outputs,
just focus on the next one.
And I'm going to use my prediction my first prediction to get the second prediction, and I'm going to use the second prediction to get my third prediction, and so forth. Yeah. Well, literally, it's the first and second because it's building up this hidden state. But yeah, good. But again, what's different? There's always going to be some data that we're inputting at each of these stages, and we have this parameterized function. This is going to be our neural network. It's going to be shared for each one of these time steps. And this is like the inductive bias, right? So one of the ways we're going to gain efficiency here is by sharing those weights from step to step.
Sharing them within a single layer or recurrent module?
Yeah, exactly.
So they're not shared, if you had multiple modules, you wouldn't share.
Right, you could have multiple modules. You can have depth. You can have depth to these things, which means that at each layer, so it's kind of, I need pictures, so I'll get ahead here to the slides. But there's two ideas here. There's this isn't really depth, but there is the recurrence from step to step in our sequential data. But there can also be depth to these modules, and those each would have their own set of each depth would have its own set of weights.
Okay. Yeah.
All right. Each layer, as we go deeper into these stacked recurrent neural networks. Oh yeah. Notice I just said this twice, and here's this the third time. We are sharing parameters. So what might this look like? It'll look something like this. What does our parameterized function look like? Well, it's going to be some linear operations. Remember, this depends on the current time step in our sequential data, and the previous hidden state. We have some sort of linear layer. That's what this is right here. We have a matrix multiplied by this vector. So implicitly there's a notion that we're going to be able to convert our time series data points into vectors, and there, we'll talk about some ways of doing that. But we're going to have a matrix vector multiplication there. Then our hidden state's also going to be a vector, and there's going to be a different set of weights there, or different matrix multiplying that. Add those things together, have some sort of nonlinear activation. Here showing a tanh, which is fairly common in recurrent neural networks, though obviously you can use a lot of different nonlinear activations. That then is our current hidden state, the new hidden state. We can just continue to run this, and then eventually we would, if we need to make a prediction, we're going to have one more layer. In this case, it's very simple, another linear layer, taking that hidden state, and then making some kind of, or producing some kind of output. Oftentimes, we want to do a classification, so this would be something like, the scores. Then actually, what we would do to train this is we would, do exactly what we've done in the past, where we apply softmax so that we get the distribution, like those scores get turned into distributions over the classes, and then the loss function at that point would be a cross entropy loss, and we would optimize in that way. This could also be, this doesn't have to be classification, it could be a regression problem or something, and we would optimize using like mean squared error losses and things like that. So like this is like, in some sense, like the most simple recurrent neural network you can imagine. And again, the important thing here is notice that these weights, these weight matrices, they don't depend on t, right? So we're using the same weight matrix for every single step in the sequence. That's the shared parameters part. Yeah.
Can x of t, I'm picturing being time. I'm picturing it as time series data.
Yeah.
But it's like maybe 10 time steps back. Like the whole, like, so then you move a step. Like,
Yeah.
Say you're typing and you say I am, and then it populates some things you could say.
Yep.
And then you give it another word, but it's going to look at I am and then the third word, right? Is that?
Yep. Yeah. So we need maybe just one more diagram to kind of make that a little bit easier to see. But yeah, think about it just in terms of training. Just think about it like in the simplest situation. Let's think of this as like many to one. We're trying to predict the sentiment of the sentence. Okay. So each of these would represent a word. Each x, so like, let's say like the sentence is 10 words long or something like that. You're going to have x1, x2, x3 through x10.
Okay, and those are all the t indices.
Yeah, those are all the, so that 1 through 10 is, each one of those corresponds to a potential t. And then we, by doing this process, we're going to have an h1, an h2, an h3, and so forth. But notice how each of the ht, so like say like h5, it depends on h4 and x5.
Oh yeah.
Right?
Okay.
So it depends both on like the current step we're at in the sentence in this case, and then as well as like the previous hidden state, which is like in some sense an aggregation of all the previous inputs, x1 through x4, through just updating this hidden state. And then we'll do that until we get to h10, and then in this many to one case, we'll use that h10 to, let's say that this is like it's sentiment analysis. We have 3 classes: positive, neutral, and negative. This would produce 3 scores, and then we apply a softmax, use cross entropy loss, and train it, optimize with respect to that loss, back propagating through this. We'll unroll the operation here so you kind of see the computation graph, but back propagating through all of the previous hidden states, and back to the input. Make sense?
Yeah.
Okay, cool.
That quick reference.
Oh, good. Any other questions? Okay, we need more pictures. Yeah, so what does this computation graph look like? This is what we were just talking about. So, whatever, this might be a word, this might be like we're thinking about weather, this might be, weather from January 1st, 2022, whatever. There's some initial hidden state. Typically we'll initialize this in some simple way, often just like zeros. It doesn't matter as long as you're consistent. That'll be like the initial hidden state, and then we'll run one step of that recurrent cell, and we'll get out H1, the next hidden state. And then we integrate that with the next data point. So maybe this is now weather on January 2nd, 2022. This function is going to take this input and give us this output, and so forth. We just keep going with this, okay? And then just like how this gets supervised depends on like which problem you're solving. So we looked at the sentiment analysis problem. Yeah, this is a reminder that we're using these weight matrices at every step. Okay, so in many-to-many, so let's say what we're trying to do, I don't know, is like classify, so like maybe these are frames of a video, and we're trying to classify, I don't know, like the action going on in each frame of the video. Clearly there's going to be some dependence, like the actions happening over here, like in the previous frame on the current frame. If I'm throwing a ball or something like that, like that's going to persist over many frames, right? And so I might supervise this in a way of saying, okay, this is like this is a classification problem. There's many actions I could have chosen. Choose the throwing the ball one here, the throwing the ball one here. Maybe eventually that changes to where I've done throwing the ball, and now I don't know. Maybe I'm sitting down. That these frames would you would be supervising each one of those frames in that way, up until you've gotten to your sort of fixed time, the length of the time, or length of the sequence.
So for this picture, I guess going back to the sentiment analysis on like a 10-word sentence. So in each of the Y1, Y2, Y3, that would be the sentiment analysis for every single word.
Yeah, so it doesn't really make sense there, because like sentiment is usually a property of like the sentence. But I don't know. This could be something like in that case. Well, this could be something like maybe like the part of speech that word like it represents, right? So it could like maybe this is a noun or a verb or I don't know, an adjective and things like that. You could learn to do things like that. It just kind of depends on the task.
Okay.
For sentiment analysis, it looks more like, I think this is the next slide. Oh, well, right. The point, so going back to the example of like, say like we're trying to classify let's call it the action amongst a bunch of actions in each one of these frames, here, then there will be a loss, so there will be a classification loss applied to each one of these outputs. And then when we're training this, each of these losses, we're gonna back propagate the error signal through these, and you can see how this final loss. Well, for this loss right here, that the error signal is only going to adjust parameters. Like it's going to adjust FW, but only through this part of the computation graph. And you can, as you move through the sequence here, and say coming all the way to the end, this is going to adjust W multiple times through each step of this computation graph. So it's kind of weird when you think about it. Like we call this unrolling. We have this recurrent cell that's kind of using the same function over and over again to build up an internal state of this sequence. But when we unroll that, what we see is that depending on the losses and where they appear, we're going to the back propagation is going to provide signal to adjust the weights, the same weights, kind of over and over and over again. And you can sort of start to see how this might learn to adjust the hidden states in a way that we build them up, we build them up correctly for whatever task we're doing here, even though that they're shared, right? Because they depend both on the current input and, the current input and the previous state, the current input and the previous state. So like those two things have to kind of play together with a shared set of weights so that we produce hidden states that allow us to do these tasks. Was there another question? Yeah.
Is each Y for like if you're many to many, so you're doing machine translation or something, wouldn't the Y one be like the weakest prediction? It hasn't had the chance to build up state.
Well, it's not necessarily like the weakest prediction. This could be a really strong prediction. It just the implicit assumption is that what we really like if we're doing something like this, what we're really interested in is building up the hidden states so that we do say like a really good job here later in the sequence. So starting with many is maybe not the best thing. I think this might be a little bit easier to reason about. Think of this as like the sentiment analysis again, or of a sentence, or maybe just like predicting like what is the action happening in this video, or we look at a couple seconds, like the frames associated with a couple seconds of video, and in this case, when you have a single output, there's going to be a single, we're going to supervise this in a single way, and with a single loss, and everything will be back propagated through this. So it's not that it'll be weaker or better. It's just what it's trying to do is use whatever information it has from the sequence up to that point to do its job. And if you're doing this, you expect everything in this sequence to help you. Like if you're many to one, you're expecting everything in the sequence to help you do this. But if you're doing many to many, you don't expect it. You're expecting everything up to that point to help you do that task at that point. And it's not better or worse. It's just that that's where you are in the task.
But then because do you combine it into many to many? You combine it into a single loss at the end.
Yeah.
But you're not like doing a fully connected layer to try and mix the Y's together at all.
No.
So like if Y1 was a prediction for like say how positive or negative the sentence, it'd be only based on the first word of your sentence, which doesn't really
Right.
make sense.
And that's not so that would be that's the wrong task. Like that's kind of like a bad question to ask, right? We're not like we typically don't want to classify the sentiment of a sentence from like only its first word, right? Well, what we typically are trying to do is classify the sentiment from all of its all the words in order. And that's why this would be a more appropriate way to set that up.
Right, but like
You're classifying articles of speech to the previous one.
Right. So, what this will learn to do, right? Like, if we were doing that, this will learn that there's like that it's typical for words like articles like the, or like nouns, or I don't know, adverbs and to show up first, right? So like those kinds of things will the encoding for this as it comes into this, plus this state saying, essentially saying I'm at the beginning. This is saying something like, hey, you're at the beginning of the sentence. It's much more likely to expect nouns or articles, right, at this point. But once you get further into this, there'll be kind of like it'll have learned to, like I've seen set, nouns and verbs in sort of this order up to this point. So now all of that state helps me to make the prediction about the next word, given, what the part of speech is, given what that word is and everything that's come before it. So it's not that like this is like a harder task or something like that. It's just It's just that you're using the sequential information to give you that. Yeah, Bruno.
Yeah, that's why like they use RNNs to like this. If they have an encoder and decoder, so you can have one set of RNNs for the encoded part. So you get a representation into something, and then once you get a fixed length vector representation using the encoder, again you use a decoder to generate the sequence.
Yeah.
If it is a translation, so you
Yeah.
have two different RNNs essentially doing this representation part where you get the context of the whole context.
Yeah, I think we will have that here. Anyways, before we move on though, do you feel like you have some greater understanding of that, or does it still feel confusing?
Well, it just seems like if you're trying to predict something about the whole, like why one cannot predict something about the whole sentence. It can only
Right.
predict something about the first part of the sentence, right? But then why T can predict things about the whole sentence.
Right. That's right. So this is not a very, the way that it's set up is not a very common setup for recurrent neural networks, because there are sort of very few tasks that look like this, that you want to make a prediction about. Some of these, you know, you want to make some prediction about like coming from each of these inputs that only depends on what's come before it. That's not a very common thing to want to do. However, let's say that we are, you know, learning to again, like classify the frames of a video. This could just be, you know, give me 60 frames, or like 2 seconds of 30 frame per second video, and just classify like the action going on in those 2 seconds. That's fine, but this actually will be helped if you actually, that task will be helped if you do have like annotation of each frame and train it to train this network, these recurrent modules, to just try to predict that action from what's come before it. That actually will strengthen the ability of this model to predict that, because it has all that additional information. But in general, like this is not a very typical way to set up problems using recurrent networks. This is very common, something about the entire sequence, right? And this is common in the kind of case that Gurunov was just expressing, where like, you know, like this is some kind of state that you want to unroll into a sequence. And typically what that is that when you're doing translation, and we'll get to this in just a second, you kind of want to encode the entire sentence that you're going to translate, and then unroll it, like, you know, turn it into a sequence. So the point is that like each of these looks very similar to each other. It's just the computation graphs are slightly different, and therefore like where the loss signal kind of is used to adjust the weights, just, you know, adjusts accordingly. Wait till we get into more like concrete examples. So sequence to sequence is different from many to many. Don't get these two confused. Many to many is really like, is this where we make a prediction for every single input. Sequence to sequence is the common case for translating from one language to another, or from just like one sequence to another. So the idea being is that we have what we typically call an encoder. So think of these as like words in the language, and we'll train this. Well, we haven't added the other side of this, but we're gonna think of this as like building up the state of this sentence, whatever it is. And then we have this hidden state here that, you know, represents the sentence. And now what we want to do is we want to have a decoder, so a different recurrent neural network that will take this, like the final hidden state from this sequence, think of this as like a sentence in French. That will be the like the initial state for this decoder recurrent neural network. And you now will want to, decode it. So this looks like the one-to-many that we were just looking at, where we unroll this into, like, say, English, where these are now the corresponding words from that. And then we train this all end-to-end by supervising basically each of the words that are predicted here to get both the correct word and in the correct order. So again, think of the hidden state as building up, up to that point, being a representation of both. So like this hidden state right here being a representation of both the encoded sentence from the other language, and then like the state we're in as we are translating it to a different language. Like, this state will give us the correct prediction for the first word in the correct translation, and then this one will give us the second correct word in the translation, and so forth. So this this hidden state both has has this information, and the fact it also at least has access to the information that we've seen this hidden state that corresponds to that output. Yeah.
So would these be like two separate layers?
Nope.
No.
No. We haven't really looked at depth yet. We can have depth. Basically, it's just, well, I have charts of it. It's easier once there's diagrams. But no, these in this case, these are all single layer. Basically, like to do depth, you now just have. I'll just say it and then we'll see it here in a second. To do depth, we had like the actual, like a representation of the actual inputs going into each one of these, but now when we go to the next layer, the inputs that are the hidden states produced here, and then it produces a second, like a second level of hidden states that also follows along, and you can keep doing that. So that's actually what depth corresponds to in recurrent neural networks. This is just like the length of the sequence. Okay, so let's get a little more concrete here. So, okay, so here's an example where we're going to do many to many, and the idea is that we want to learn to like produce English sentences essentially, or English words and English sentences. So so here this is just kind of a simple setup, and this will become a little more complicated in just a second, or not complicated, that's the wrong word, a little more complex in just a second as we add more to the vocabulary. But the idea here is, we want to be able to learn to produce the word hello and other English words. So the word hello, think of each of the characters. These are our inputs. Remember that these have to become vectors to go into our neural network. So we can't just input a raw character. These need to be some kind of vector to go into the recurrent neural network because we're going to multiply it with a matrix. So here's a very simple one-hot encoding, as it's often referred to, of this. This is not typically the way that you would want to do this. You can do this, but there are better ways of learning, especially for larger vocabulary, dense vector representations of these things. But anyways, this works. It is a representation. So that's your input layer. Now, what does this look like? Well, this is going to be integrated with. We're going to take this vector, multiply it by whatever the weights are right now for the input matrix. There's going to be some initial hidden state. Often it's just zeros. We're going to multiply that with the hidden matrix, the hidden state matrix. and then we're going to apply our nonlinear activation, and that's going to give us our hidden state at that point in the sequence. So in this case, you know, whatever the weights ended up being, this was the output H1. Okay, so this is X1. Let's just say H0 was all zeros. This is now H1. In the next step, we're going to again do the very same thing, except that this will be X2 times that weight matrix. We'll now use H1, this right here, times this weight matrix, and then we'll run that through our nonlinear activation, and we'll get that vector and so forth. Okay? Yeah.
Just to be clear, WHH and WXH are the same matrix?
No, they're different matrices. That's why they have these different indices. I mean, it's just what this is trying to show is that we're going from input to the hidden state, right? So like think of it this way, like the input dimension, it's like the size of the vectors for the inputs might be in this, you know, it's 4 in this case, but the hidden state might be, I don't know, 64, right? So this is a matrix that takes you from, you know, from vectors of this size to vectors of the right size, you know. So it's going from X to H. That's why it's like that. This is going from H to H. So this would be a square matrix going from 64 to 64. But they're two separate matrices. So it's not that those two matrices they're sharing parameters. It's that when at every step here we use the same matrices,
Gotcha.
even though the T is changing. Yeah.
Actually, and one more question. What is the goal here? Or is this
Yeah.
not really
So what we're going to do is we're going to learn to produce. So this is like a canonical many-to-many example. We're going to learn to produce the next letter in the word, or in a full sentence in the sentence.
Okay.
So we're slowly getting there. Okay. So now, from this hidden state, we now want to multiply by yet another matrix to give us the scores. Here are our scores. Okay. Remember, this was, if we go way back to this right here. This is, you know, our final hidden, or well, just the current hidden state. We're multiplying it by W, by a different W that's taking us from the hidden state to the output state. So going back, these are our scores. Would, you know, now apply softmax. You know, use cross entropy loss, and what we're trying to do, remember, is the signal we're supervising with here is the next letter, right? So we're trying to get this thing to, just think of this as like one example in like all of the English words or sentences that you could see. If we want to do this character by character, we want, you know, in general, we want H to produce, well, this is going to be a distribution. So like after you've trained it on a whole bunch of words, not just hello, but all the words in the language, this is going to be some kind of distribution that says, you know, what's likely to follow H given like what's come before. And if this is the first sentence, or the first letter in like my sentence, this might just be like a naive distribution over like, you know, all of the like where the, you know, like the frequencies here might correspond to just how often each letter follows H, right? So like, I don't know, like what letter would not follow H? Like Q. Yeah, I don't know. You know, I think Q might, I don't know. There's probably, but it's probably unlikely, you know, like letters like, I don't know, Q or Z or something like that to follow. So like they would have very low probabilities. But you know, like vowels like E would be very likely to, you know, to appear next, right? So like that would, you'd hopefully learn that from your corpus of data. And you know, this is going to learn to produce, you know, that distribution. And then you're going to, you could do two different things here. So when you're supervising it, you're going to say, you know, this is the correct output. So when we do back propagation, we're going to try to make this score the largest, right? That's the whole classification, you know, binary, or not binary, but cross entropy loss. And we're going to produce that. When like anticipating a little bit here, when we're at like at inference time when we're actually like generating a sentence, this will be a distribution that we can just sample from, you know, according to the probabilities in there. And like maybe at some points we'll get an E, at other points we'll get an O or something like that. And then we'll continue to run this forward. So when we're training it, you know, in this case, the correct letter to produce is E. Remember that it corresponds to, you know, the second letter in this way of representing letters, and so that's why this is green and show, you know, that's why that the second entry is in green, because that's the correct score, or like that's the score associated with the correct class. Notice that it's not currently the largest score, so when there's an error there, so when we do back propagation, we have to adjust the weights for this, right? But then we just keep going, right? So now we know that there's an H. That's essentially what like this is saying right here. We integrate, we bring that information together with the fact that we now have an E. You know, we do our multiplication of the two matrices, or application of tanh, then we apply our other matrix taking us to the scores, and we again get another vector of scores. When we supervise this, the next letter is L, so that's going to be the correct letter to supervise with. That's why this is shown here in green, because it's represented by the third character here. And we will, you know, again, it's incorrect because it's not the largest score. So that will have error to back propagate, and so forth. You know, the state here now represents essentially that we've had an H and an E, and so now we're going to take that state, integrate that with the fact that we've got an L, do the same step. The next letter we want it to produce is an L, so again, we're going to supervise this in such a way that this gives us the highest score. Notice that it is already, I mean, if you remember cross entropy, there's always some signal, but that's, you know, the error signal there is is far less because we have it correct. This might push it to be larger, but it's correct, and so forth. Okay? And then the word here is hello, so we supervise this final, the final state here with the letter O. And then, so remember, each one of these is a classification problem. All of these losses from each of those classification problems come together into, excuse me, we're going to add them all together into a total loss, back propagate through all of these, you know, the different signals through all of these appropriate errors in this computation graph. To adjust the W's here going from hidden states to scores, the W's here going from hidden states to hidden states, and the W's here going from hidden states going from inputs to hidden states. And in such a way that it should be very likely for this thing to produce a word like hello and not just some scrambled set of letters like H, Z, Q, you know, K, whatever. Yeah.
So I guess one of my confusions is that the WHH matrix is the exact same for all of them. Does that mean it's only dependent on the letter that comes before it?
No. Remember, what is this? What's the way to think about the hidden state? So these hidden states, as you go from input to input, is that it's accumulating the state of whatever's here.
Oh, those get multiplied by the matrix, or by the hidden matrix.
Yeah. So like this hidden state here has information about, you know, about
E and H.
Yeah, about E from the input and H from before.
Gotcha. Okay.
And this one has information about L from the input and HE from this hidden state here.
Yeah. Thank you.
So like that's the whole point of this right here, is that it's keeping state basically. And yes, you could have a different W for each one of these, like for each one of these state transitions. It'd be far less efficient, and in some sense it would be learning, like you'd have the hidden states here would sort of would have a different meaning basically. Like they're hidden states still, and you could think of them as accumulating information, but but you could think of some of that information as being like kept in the weights of each of these matrices here, instead of it being in the hidden state itself. So when you do it this way, you're forcing the W, like sharing the same weight matrix from step to step here, is you're forcing the W to be about transitions only, and the hidden states to really be about the accumulation of the state, integrating that with the current input in the sequence. So it's just that's the thing that we call inductive bias. Like that's the inductive bias. Like that's if you were to change that and have a different W for each one of these, you'd have a different inductive bias. Why we call it that? I mean, there's a reason why we call it that, but it's a different way of expecting to get information from the sequence, to extract information from the sequence. But great questions. They're great. Other questions? Okay. Yeah, so like I was saying, at test time, so at inference time, when you want to actually produce, in this case, a sequence. So sorry, step back. Many to many. Kind of like going back to the question I was asked earlier. We only want to be able to use what's come before in the sentence to predict what comes next, because we want to use this in some sense to like generate text or generate text. So generate characters, and we hope that this is good enough that it's actually generating like meaningful meaning that from character to character it's somehow meaningful. So if let's say this has been trained on everything, all possible English language examples, or maybe we just we've chosen from some certain corpus, maybe of just like ancient texts, or maybe just like what's on Wikipedia, or maybe we'll look at some examples here in a second. But when we run this at inference time, we do what we did during training, except that when we get to this point here, we turn these into we apply the softmax, and we think of this as now a distribution and we want to sample this. I think this is like the parameters for multinomial distribution, right? Where this is the probability that an H follows next, and this is the probability that an E follows next, and an L and an O. And so, you're most likely to sample the thing with the most probability, but because it's a distribution, you may you won't sample anything with a 0 probability, but you may sample something with like a low probability, but not very often, right? But again, this depends on the hidden state. And then when we go to the next one, whatever we predicted here now becomes the input in the next state, right? So like, unlike at training time when we had a whole word here and we knew what the answer should be, here we just when we're generating, we're literally just taking whatever the prediction is for the next step, using it as input, and then running this forward, hoping we get something like hello, or just something that isn't gibberish. Wait, let's make sure that we have. Yeah, okay, good. We have examples here coming up.
Could you go back to
Yeah.
the previous slide? So when you say you're sampling from that softmax.
Yep.
So you're not just taking the highest score. So I guess
You could take the highest score, but that would be like deterministic in some sense, right? So you just get the same, like for however you seed this, you would just get the same output every single time. If you sample from this, you're going to get different outputs, depending on the random chance of sampling from these different characters with respect to these probabilities.
Well, so do you run this multiple times? So say
You could. That's like the fun of it, right? Is like I could put H in here and I could get it to say hello, and I could put H in again. I could say happy.
Okay, yeah. Because you could predict H-O.
Yeah.
First.
That's right.
And then it would go with O.
Yeah, and it might say, how are you? I don't know, you know what I mean?
Okay.
Like that's what you're.
Your phone kind of does that when you're typing.
Yeah, that's right. And it used to use these kinds of models for that. Now it uses transformers, distilled transformers that are way better. But yeah, that's right. That's exactly what it's doing. Yeah. So we get to examples here real quick that hopefully we'll start to put some of the abstract ideas together here. But again, remember what's happening here is that when we're doing something like this many-to-many, we have like a really dense computation graph, right? Like, you know, from every single hidden state we have an output. Each one of those is being supervised in some way. Those all kind of combine into one large loss. And then back propagation, basically, you know, every arrow we can walk back. You know, we start here from like the final one. You know, we're going to back propagate through the weights here, and then the weights here, and then so forth this way. The weights here, and so forth. Basically, the point being that like there is however long the sequence is, this is becoming like the longer it gets, the more computation is required to do back propagation in this sense, or in this case of many to many, and in all the cases, but like this is like the most extreme. And this actually for long sequences, this can be very like onerous. Like this can be very costly for doing back propagation. It can be in two ways. It can be very time consuming because there's just so many paths to go through, and kind of redundant paths. And the other thing is that, as you can imagine, depending on like activations you choose and some of the other things that we learned about when we were first studying back propagation, we can really have our loss signal, like those gradients, attenuate quite a bit, as we move back through this computation graph. So you can imagine that like the effect of the loss coming from this final output here would probably not have much. It would very likely have very little effect on these kind of earlier hidden states because of just the distance it has to travel, like those gradients have to travel in terms of the computation graph.
So this is a linear network, right? Because we're not using any Rayleigh.
Well, so you could use Rayleigh, but remember there was a tangent there. There was a hyperbolic.
Oh, that's right.
And the reason we're doing that is like that's like the sort of like the early plain vanilla recurrent neural networks use tangent. And actually, some of the more sophisticated ones still use like tangent, but you could have a Rayleigh there. Yeah. Anyways, that signal can attenuate, and so yeah, you can play some of the games that we played before, like change the activation functions, and think about like sizes of hidden states and things like that. One of the things that's very common to do in these unrolled computation graphs for recurrent neural networks is to do truncated back propagation. So instead of back propagating through every single state, during the forward pass everything's the same, but during the backward pass we only like propagate the gradient signal to like a certain number of steps back from where it was, and say that's good enough. And usually your training could take a bit of a hit in terms of like not lowering the loss to the minimum that you could, but usually for all like practical purposes this is far more efficient and it performs about the same. It's very, very common. You'll see in like your deep learning frameworks that you have the option to do this kind of truncated back propagation, just like an option. Okay, so let's look at some examples. So let's do this character-to-character, many-to-many problem. And let's just train it on something interesting. So the examples we're going to look at now are just all of the recorded sonnets attributed to Shakespeare. Okay? So Shakespeare has a very kind of distinguishable style. Like, obviously, the English is older to us, so, kind of has that. Sonnets have a kind of rhythm to them. They're about certain kinds of things. They're not, they're not just about everything on the planet, but they're about certain kinds of topics and themes. And what we hope is that, and there tends to be a lot of sonnets, right? Or there are a lot of sonnets from Shakespeare. I don't know how many there are, but in the sense of like number of like character to character, pairs, like number of sentences here, there's quite a few examples. So we hope that if we train even a simple recurrent neural network on the sonnets of William Shakespeare, that it will learn to produce not just like recognizable English, but English in the style of Shakespeare writing a sonnet. Okay? So what does this look like? Well, we start training this. So like, we randomize initially all the weights in these shared networks, and we train a little bit, and this is what we get. So we don't see a whole lot of structure at first, right? And that makes a lot of sense, right? Like this hasn't had a lot of opportunity to adjust the weights, given the errors it's making in these losses. And yes, it's producing sequences of characters because that's like what it's constrained to do, but there's very little structure there. Train a little bit more. This is kind of fun to play with to see like how much training is required. Like think of this as like epochs going through all the sonnets. Train a little more. This is still mostly gibberish, but you see some of the statistical patterns of English language starting to show up, right? So, for instance, in this first example, like kind of like where the spaces occur sort of don't make sense, right? Like there's two spaces right here in this very first example, right? Like there's like 3 spaces there. Like that never happens, right? So like this is really undertrained. But you can see that in this example, all of a sudden there's only ever just like a single space, right? And then another character. So it's going to learn the statistics of that pattern, that if I have a space, then the thing that happens next is a non-space character, a non-white space character. It's also learned to put a space after a punctuation. It's kind of learned that there's, like, with quotes, that there should be like an opening and a closing quote, although that's not totally the case because there's just a single quote here at the end. Although you kind of think about the fact that there's probably like a lot of examples where the thing you're producing ends with a quote. It's also like the length of the words seem to be a little more believable than like what was up above, right? So it's starting to get some of these patterns of what English language is like, at least according to Shakespeare. But we don't recognize really the words yet. Although, I don't know, this might be a proper noun. It's interesting that this single letter I shows up. I mean, this shows up a lot in these sonnets, right? So like it's learned that. But kind of nonsensical. Keep going, train some more. This starts to look a lot more like English. Like if you just kind of glance at it like without trying to really get the sense of it, like it looks like English, like there's certain words that you see right away that like are just right. Very common words like that, me, of, for, haul, like her, and things that show up a lot, like it's learned to produce them correctly with spaces on either side. It's interesting that it's even got this like possessive, apostrophe s on what looks like a proper name, correct. But a lot of the words, even though they kind of have like the right size and kind of look like they might be words, like like if you first look at this, we're like, oh yeah, that's probably a word. But then you look at it closer, like what's after? It's not actually a word, but it's pretty close to what might be a word. So it's getting better, right? It seems to be. It's with more and more training, it's getting more and more actual words. They look more like just like the spacing of like the words and such looks like English, but again, it's not quite right, especially because there's really no meaning here. And then you just keep going, and at some point this starts to actually get quite good. After enough epochs, what does this look like? Well, you have kind of like all the words. I think in this example, all the words are actual words, except for maybe a king here. but maybe there's an old English word that came that I don't know about. But most of the words are recognizable, and if you read it, like it reads like a sonnet as well, right? Like this doesn't really make sense. Why do what that day? But if you look at a lot of the sonnets, there's a lot of like asking yourself questions, you know, contemplating. So like this is almost like asking a kind of like introspective question. Why that day? You know, whatever. But you know, it's got things like it's followed by, you know, there's a comma here. It's followed by a replied, a proper, you know, noun for a person, and so forth. And wishing to himself the fact that the Princess Mary, was easier fed in than often to him. I mean, like, again, it doesn't quite make sense in terms of like there being meaning there, but it's looking more and more like English. And if we keep going, we can hope to get this to be a lot better. Actually, for like simple recurrent neural networks like we're using here, this is probably as good as it's going to get. So it got pretty good, but it's not exactly like producing meaningful like sonnets.
So like on the first step, like how are you calculating loss on something like that?
Everything's got a whole bunch of, you know, every single thing there's got some kind of error it's propagating back, right? Like
Yeah.
There's just so much that's wrong there. There's just a lot of error. But the loss is huge.
Like if it were like, I don't know, do you have, in this type of case, do you have like a target? Aside from the data that you're feeding into it as you go through the
Like a target loss you want to get to?
Yeah, it's like if you had like 3 classes and you're like, no, that's the wrong class, so that incurs error, and then that's part of like the loss.
I mean, there is a kind of a way to think about the error in terms of like like how Englishy it is, but really it's like, yeah, like many generative examples, which is what this is, like we're generating stuff, like it's really evaluated by, you know, you and me kind of qualitatively looking at it and saying, oh, that's pretty good.
Okay, that answers.
Or like, oh, that's better. You know?
That answers my question.
And when we start to look at generative models for like images, it'll be exactly the same thing. We'll look at these images and we'll be like, oh yeah, that's better than this because, I don't know, it's crisp. It just kind of looks like what I expect like an image of a face to look like. And that one, it's still there's a face, but it's like far worse, right? So it's very qualitative. I mean, there are ways of quantifying it, but they're sort of, it's very qualitative.
That answers my question.
Yeah. Okay. Good. Yeah.
But then, before when we were doing image classification, we had a set of training images and a set of training labels.
Right.
So in this case, do we have a set of, like, what are the sets?
Yeah. So this is an example of what you might like these days is called self-supervision. So remember what we're doing is we're taking like one of these sentences, and that's going to be the input, and the output, when it's many to many, is going to be that same sentence but shifted, like you're going to take off the first character and shift to the left. So that what you're doing is you're predicting, like you're supervising the network with the next character. So like for each one of those characters, the thing it should produce, the thing it should predict, is the next character in that, like in this case, the song, like the sentence from the sonnet. Okay? Yeah.
Were these fed in like whole sonnets at a time? So one whole sonnet?
No,
at a time?
like lines of the sonnets, basically. It would be the typical way to do that. Yeah. Like one of the drawbacks from of especially plain vanilla recurrent neural networks is that they aren't able to like build up state for very long, like appropriately for very long inputs. So you need it needs to be like a reasonable size, maybe like 20 or 30 or less, like in the input.
Okay. But it does seem to do pretty well with remembering like where quotes are.
Yeah, I mean it's learned those statistics from seeing a whole bunch of these sentences, right? Yeah, yeah. It's the magic of neural networks. It actually is really remarkable. Like this is, if you were to try to like again do this by hand, this is really tricky to do. Even if you were to do the, like one way to think about this would be to pre-compute all of the conditional probabilities of like the next character given like n-grams, you know, like certain maybe like 3 grams, right? So like triplets of triplets of characters, like what, you know, what should follow, and you can you could literally go to the corpus and compute all those. The trouble is that it would be extremely sparse. Like, you know, for each triplet, like the triplets maybe not so sparse, but like you wouldn't see every single triplet very often, you know, like very often, and you know it would be followed, and then what follows would, you know, like that it ends up being like a sparse representation of these of the language. This doesn't rely on sort of like fixed notions of like n-grams or something like that. It's really just like learning to just take whatever the signal is, adjust weight so that, you know, whether it needs, you know, the trigram coming before, if it needs something far more sophisticated, like many, you know, seeing many characters built up over that sequence, you know, like it can learn to do that. And that's kind of like, again, like the power of neural networks, differentiable programming. We can go through other examples here. You can look at these in the notes, but you can get kind of more, like, you can get kind of crazy here. You can, so for instance, anything that's sequential like this, you can learn to, like sequential characters, you can learn to do this. So if you're, you know, if you're like me and you did mathematics for your degree, you learned LaTeX at some point to typeset all of your math, and even though this is like very sophisticated, again, it's just like a sequence of characters. So you can actually train these things on LaTeX source code, even really like crazy mathematical LaTeX source code, and produce what looks like you know, like reasonable LaTeX, right? In fact, I can't remember what year this was, but there was, once these started getting kind of good, people were generating, like they were training on like all the papers in a certain subject, and they were generating new papers from all these old papers and submitting them to conferences, and very often they were being accepted, even though they were like complete gibberish. The example is like really, it's really interesting. It says a lot about a lot of things, but you know, like, you know, this kind of looks mathematical, but if you know like the area, you know that this is like complete hooey, you know, like that. Like these diagrams don't mean anything, but anyways, you know, it can learn to do interesting things like this. Why not train this on the entire, you know, Linux source code? That's all out there. Here you go. This is generated code from you know, training on Linux. So it's got nice C formatting. Do command as a function name is like really interesting. It's like very generic, right? Again, like this probably doesn't compile, but it does look statistically like C code. If any of you been, you know, kind of been paying attention to what's happened in this area, you might have learned or even used Copilot, like in Visual Studio Code, and it's basically what it does is takes it was initially trained on just like all the Python source code on GitHub, open on GitHub, and it learned to take doc strings and then produce the Python code that was associated with that doc string, which is again like it's a sequence to sequence idea, but in this case they're using transformers because to do something like that and have it be useful, the recurrent neural networks just don't rise to the task. It even learns to produce these awful header files. Yeah. And then finally, and we won't watch this. We don't have the time, but you know, I encourage you if you haven't done it yet, because this was in like the first lecture. Is again, this is the production. It's about a 10-minute film of a script that was trained on all sci-fi scripts, at least they could get their hands on. It produced a sci-fi script, and then they got some decent actors to actually act it out and produce it. And you know, it's really comical. Like it definitely feels like science fiction, especially when you're watching this and they have like, I don't know, goofy science fiction sets and clothes and things like that. But you know, it doesn't sound like a coherent script, but statistically, it's definitely sci-fi. You definitely can get the sense of it, you know, and it's definitely got like, you know, themes from sci-fi and things. So it's really quite interesting. It's not really using anything more. It has a better recurrent neural network that we're going to be learning about, but it's basically just trained in exactly the same way that we just saw today. So lots of cool party tricks you can do with this. And yeah, that's it for today. Thanks.